The midpoint theorem states that the line segment connecting the midpoints of two sides of a triangle is parallel to the third side and is half its length. Today, we will derive this theorem step by step using vector algebra. We will first set up our triangle using position vectors, then define the midpoints, perform vector operations, and finally simplify to prove the theorem. First, let's visualize a triangle ABC in a plane. We choose an origin point, let's call it O, which can be anywhere. Each vertex of our triangle, A, B, and C, can be represented by a position vector from the origin. So, we have vector OA, vector OB, and vector OC for the vertices. Now, let D be the midpoint of side AB. The position vector of midpoint D, vector OD, is found by averaging the position vectors of A and B. So, vector OD equals 1/2 times the sum of vector OA and vector OB. Next, let E be the midpoint of side AC. Similarly, the position vector of midpoint E, vector OE, is 1/2 times the sum of vector OA and vector OC. Our goal is to analyze the vector DE, which connects these two midpoints. We can express vector DE as the difference between the position vector of E and the position vector of D. So, vector DE equals vector OE minus vector OD. Now, substitute the expressions for vector OE and vector OD that we just defined. Vector DE equals 1/2 times vector OA plus vector OC minus 1/2 times vector OA plus vector OB. We can factor out the 1/2 from the entire expression. So, vector DE equals 1/2 times vector OA plus vector OC minus vector OA minus vector OB. Notice that vector OA and minus vector OA cancel each other out. This simplifies the expression to vector DE equals 1/2 times vector OC minus vector OB. Recall that the vector representing the side BC is found by subtracting the position vector of B from the position vector of C. Therefore, vector BC equals vector OC minus vector OB. By substituting this back, we find that vector DE equals 1/2 times vector BC. This equation tells us two crucial things about the line segment DE relative to BC. Since vector DE is a scalar multiple of vector BC, specifically 1/2, it means they are parallel. Also, the magnitude, or length, of vector DE is exactly half the magnitude of vector BC. This precisely proves both parts of the midpoint theorem using vector derivation. Let's use this method to check another pair of midpoints. Imagine F is the midpoint of BC, and E is still the midpoint of AC. We would define vector OF as 1/2 times vector OB plus vector OC. Then, vector EF would be vector OF minus vector OE. After substitution and simplification, we would find vector EF equals 1/2 times vector OB minus vector OA. This shows vector EF is 1/2 times vector AB, meaning EF is parallel to AB and half its length. This vector method provides an elegant and systematic way to prove geometric theorems. In summary, by representing vertices as position vectors and midpoints as averages of these vectors, we directly showed the relationship. We proved that the segment connecting midpoints D and E is parallel to side BC in half its length, confirming the theorem. This vector approach simplifies complex geometric proofs and highlights the power of vectors in analytical geometry. Generate your own educational videos for free at eduvids.vercel.app.